This is my code for LAB05. Before I go into it, I'm going to go over some of the calculations that were needed beforehand. So our Romi Robot has to travel in a triangle, and we know that side A will be 100 centimeters, and we know that beta is going to be 30 degrees plus the last digit of our 800 number. In my case, it's 3, so my beta is going to be 33. And knowing that we have a right triangle, that leaves alpha to be 57 degrees, as we have here. We can use cosine to find our hypotenuse, or our C, the long end. That comes out for me being 119.236, or approximately 119. Using the Pythagorean theorem, we can find B, and for me that is going to be approximately 65 centimeters. Perhaps the most important part will be these next two angles. My robot has to travel up to here and then make a turn and go this direction. So that's equivalent to 180 minus beta. So that will come out to be 147 degrees. Going in this direction and going around alpha, that's going to be 180 minus alpha, and that's going to be 123 degrees. Of course, to return to the original position, it's going to be 90 degrees. Out of curiosity, I just wanted to see how many pulses it would take to do a 147 degree turn. Using the equations we learned in class, it turned out to be 1,184 approximately. For a 123 degree turn, it will be approximately 991 pulses, and for 90 degrees, 725. So we'll go over the code. Our static variables, my wheel diameter is closer to 6.95. For the calculations, I'll need to include the wheelbase, which is 14 centimeters. Counts per revolution was given to us, calculated in the example, as 1437. My first turn, second turn, and third turns are going to be 147, 123, and 90 degrees respectively. Which we just went over. Distance 1, distance 2, distance 3 will be 100, 119, and 65 centimeters. Again, that was covered in the calculations. Difference is 0. I can probably just get rid of this, but I'm going to leave it in. That is the difference between pulse counts in the left and right motors. Right now I'm keeping it 0. It's essentially not there, but still, I haven't decided to take it out yet. Max speed, I set up 254. That's mainly because when I'm testing out the code and I'm incrementing speeds, I don't want something to go wrong and it just exponentially go high and damage the motor. I set a minimum speed to 30. Under that, motors don't seem to work properly anyway. I have a button delay of 2 seconds. And this serial delay 1, I have a 2 milliseconds. And the reason I did that is during the debugging phase, I had serial prints and eventually got the code working. I was pretty proud of the code I had working. However, when I went and took out the serial prints for submission, the code that we'll use for submission, the code acted differently, and it turned out it needed some of the delays caused by the serial prints. So you'll see in this code, and I'll point it out a little later, I had to go back in and I just added a small delay. Here's 2 milliseconds. For some of our dynamic variables, I'm setting the left and right motors pulses to 40. Obviously, it works a little better when it's not going too fast. So in our setup, we just basically wait for button A to be pressed. Once it's pressed, we go into our void loop. We have a delay, which you said was 2 seconds. And we have our functions here. We have our first straightaway, which is 100 centimeters. Our first turn, which will be 147 degrees. Our second straightaway, which is going to be approximately 119 centimeters. Our second turn, which is 123 degrees. Our third straightaway, 65 centimeters, and then our third turn is 90 degrees. We'll go into they're virtually the same, but we'll go into the first straightaway function. So what happens here is we reset the left and right motor encoder pulse counts. We then need to determine the number of pulses we need to go that 100 centimeters. So down at the bottom, this was provided to us as an example. It's a count for distance function, which using the float of the wheel diameter, counts per revolution, and distance. It's taking the wheel diameter, timesing it by pi, and then it's dividing by the counts per revolution. It's then using that to find the distance divided by that temporary number that we got. Then that's probably a float, so we want to return the integer of that. We will then use that to determine the number of pulses that we need to go exactly 100 centimeters. So then I will call a let's go straight function. This let's go straight function is going to be the same for the first, second, and third straightaway functions. So we'll look at that real quick. In the let's go straight function, while this condition is true, being that the left or right motor counts are less than the number of pulses needed for 100 centimeters, we will be going through this setup here. So we get the left and right encoder counts, we set the motor speeds, and this is the difference I was talking about. Right now it's set to 0, but if the left motor count is less than the right motor count, we're going to speed up the motor and we're going to increment it. This serial delay 1, now actually let me go over the second part. And if the left motor count is higher than the right motor count plus difference is 0, I am going to slow down the motor and we'll decrement it. Serial delay 1 here, this is where I was printing out what was happening during this instance. When I removed it, the code did not work, or the robot did not perform as good as it had with the serial prints. It turned out the serial prints, delay caused by that serial prints was needed during this motor change. I'm not 100% sure why yet, but I'll keep looking into that. And let's see. So that was for the go straight function. And once, let me go back to that. So once this condition is no longer true, this while function here, we will then stop the motors, then we'll move on to the next function within the void loop, which is our first turn, which is turning 147 degrees. So first turn will be similar to our second turn and third turn. Again, we will reset the left and right motor counts, and then we need the number of pulses to make that 147 degree turn. So there's a function here called count for turn. This is basically, I just modified the example given to us for count for distance. In count for turn, I'm taking the flow of the wheel diameter that counts per revolution, turn, which is the degree that I'll be turning, and base, which is the wheelbase. So I call this a temporary 2, and I have the degree divided by 360 times the base divided by the wheel diameter times the count per revolution. That's a float, but I need to return an integer, and that's temp2. So we use that to get the number of pulses to go 147 degrees. Then we'll go for the let's go straight function. This function here, let's go, sorry, not let's go straight. That's straight away. This is where we need first turn. So we get the number of pulses for the first turn. We have the wheel diameter, count per revolution, first turn, and wheelbase. We use that to determine the amount of pulses we need for that turn. It then calls the let's turn function. This let's turn function is going to be the same for the first turn, second turn, and third turn. So we'll look at that real quick. Let's turn. Similarly here, we have a while condition here. If the count of the left is if the count for the left encoder is less than the number of pulses we need, or if the negative right is less than the negative pulses. And it's not negative, it's just that we're reading the pulses, it's coming through as negative just because it's going the opposite, one of the wheels is going the opposite direction. So we'll get the left and right encoder counts, we'll set the speeds, motor speeds, left speed, negative, right. It's not really negative, it's going in the backwards direction is what I should say. So here, if the absolute left motoring count plus the difference of 0 is less than the absolute count on the right, and we say absolute because again the motor count when it comes through is kind of negative. So even though it's just backwards. Anyway, if the left count falls behind the right count, we will speed up. Again, there's the serial delay. That's where in my other code I had some serial prints that were more important than I thought. Then we set the motor speed. We'll increment the motor speed of the left side, and we'll just set the right speed in the backwards direction. Likewise, if the left count goes ahead of the right count, we will slow down the motor, we'll decrement it. Once this condition is no longer true, we will stop the motors here, and then we'll move into our next function within the loop, void loop. And here, see our first turn. So then after the first turn, we'll go right into our second straightaway, which we said is 119. So first, second, and third, same. They're all the same function basically, except their distance. The first, second, and third terms are basically all the same except for their degrees. However, the third term, and I'll just show you the one difference in the third term. Let's see here. In the third turn, once it's finished, it will stay here. It will stop until button A is pressed again. Once button A is pressed again, it will then repeat everything in this loop here. So here's our robot. I've removed the front caster. I'm still trying to hone in on the best weight. I still haven't done that. That's one of the reasons we'll be testing at 40 motor pulses. But let's go ahead and upload this code. And see, oh, I just checked it. Now I'll upload the code. Okay, we're done uploading. So real quick, I'll show you the course and what's going on here. So this tape measure here represents the, I believe it's side A of the triangle. It's 100 centimeters. It's hard to see this, but this black ruler represent, if you go back to the center, you can kind of see it is, let me move this just a tiny bit, it's roughly 65 millimeters. So from here to this middle point, 65 centimeters. And then we have, this is roughly the 33-degree angle. This is direction of the angle. This piece of tape is not 100% perfect. It probably should be a little over, but anyway, we know when our robot turns, it needs to kind of be facing, the toothpick needs to be facing this direction. Basically, when it makes the turn, it needs to kind of turn that direction. So I'll move this over here. When we get to here, what we're hoping that is when our robot gets here, we're hoping that the center of this robot is right over this center right here. And we're hoping it will turn, then go back to our starting point, and then back into our original position. So we'll get ready to test this. Set up here. position the robot over the line. Turn it on. And I will press the button. 1, 2. So we'll take a look here. Pretty straight. And we're heading to our turn point. Again, this tape is not 100% accurate, but so pretty good. We're getting to our point. Again, we're hoping that the robot's center will stop over the center of that. Looks good so far. Perfect. Almost. We'll see. Oh, yes. Very good. You see we're heading right onto the line here. Right on the line. Perfect. So let's take measurements here. Let's see, this is 20 millimeters, or 2 centimeters. I'll put that right here. And we can see that it's really dead on. Not really much any deviation there. Big deviation may be on the center where the wheels. It looks like perhaps I'm going to say about 12 millimeters off from center. That's on the right wheel. And then left wheel is a little, I'm guessing it's also going to be about 12 centimeters. And it does look to be about 12 centimeters. Excuse me, 12 millimeters. Well, less than that, actually. Hold on. It's actually about 5 millimeters on the left side. And yeah, actually about 5 millimeters off on the right side, sorry. So overall, really good results with this, with LAB05, so I'm really pleased with that.